So now we have all the basics. Let's look to see what happens in our bag of gametes, looking at the sperm and eggs, our gene pool. So we can have two different types of sperm, big A sperm and little a sperm. We can also have two different kinds of eggs, big A eggs and little a eggs. And the frequency at which we find these different classes is going to be the same as the frequency of these alleles in the population. Remember, we call the frequency of the alleles P for the frequency of the big A and Q for the frequency of the little a. So that means that the frequencies of the sperm and eggs will be P for the ones with big A and Q for the ones with little a. So you can be either a sperm or an egg and be a big A, either a sperm or an egg and be a Q. And we're not going to really care for now about the different relative amounts of sperm and eggs, because in this population, we're going to have this equal frequency of alleles in the sperm and the eggs, so we can just stick them all together in our big bag of gametes and treat them more or less the same. And again, that's because we have random mating. If we didn't have random mating, that would potentially not be the case, and it would actually matter if it was the sperm or the egg that we are thinking about. All right, here's my bag of gametes, my gene pool. It's my little circle around it. So I want to think about what we're going to see in the next generation. So what's the probability of the different genotypes? Okay, the probability of each genotype. And we can figure these out by doing a sort of a Punnett Square. This isn't a regular old Mendelian Punnett Square, because in this case we're thinking about the frequency of genotypes in a whole population, and not just the frequency of genotypes from one specific mating. But we can still do it a lot in the same way that we do a typical Punnett Square. So to figure this out, we're gonna set up our Punnett Square, and we're gonna use that to think about combining these different frequencies. So what is the frequency? What is the likelihood of combining a big A egg and a big A sperm? So that's going to be an and statement in probability. In an and statement, we have to have this and that happen. We have to flip two coins and they both get head, so a head and a head. So when we have an and statement like that in probability, we multiply the two numbers together. So the probability of flipping two coins and getting two heads is 0.5 times 0.5 or 0.25. So with our and statements in probability, we multiply the two numbers together. So we're going to multiply them together if we say and. If we need two independent events happening at the same time, we can multiply them together. Okay. And in this case, we treat these as independent, again, because we have random mating. The other kind of relationship we can have is an or relationship, where we get a big A sperm or a little a sperm. And in that case, we're going to add these probabilities together. So for example, the probability of getting a big A sperm or a little a sperm is 0.5 plus 0.5 if they're equal frequencies of both, which is 1, which is what we know it should be. P plus Q equals to 1. So or statements, we are going to add them together. So I just want to mention that before we go and start drawing our little Punnett Square, because that's going to come up in just a second. All right, so here is our little square, and we're going to put the sperm along one axis and the eggs along the other axis. And this is what we do with a regular Punnett Square as well, only in those cases we're talking about a single sperm and a single egg. Here we're talking about a huge gene pool of these. So these are just the allele frequency, the alleles for either the sperm, big A or little a, and the egg, big A or little a. Now I'm going to fill in what we get. So this is what happens if a big A sperm meets a big A egg. We get a big A individual zygote resulting from that. We can fill in the whole Punnett Square chart in this way. Okay, so this square, again, this represents a big A sperm and a big A egg getting together to form a zygote. So what is the probability of getting this? What's the frequency we expect this at? Well, the frequency of the big A sperms is P. So that's the probability of getting one big A sperm out of our big bag of sperms. And that's the same as the probability of getting one big A egg out of our big bag of eggs. It's also P. So we have an and statement here. So we're thinking about P and P. So getting a big A sperm and a big A egg. So we multiply these two numbers together. So this is going to be P squared. Same thing for a little a, little a. We're going to have the probability of Q getting a little a times the probability of Q getting another little a. So little a sperm frequency times the little a egg frequency, Q times Q. We've got two possibilities left, but they're both going to give us the same genotype. So that's going to get interesting. That's going to be big A egg, with little a sperm, or big A sperm with little a egg. And in either case, the probability is going to be the same. The probability of getting one big A, which is P, times the probability of getting one little a, which is Q. And we multiply these together because we need a big A and a little a to make this happen. So P times Q. Okay. So the overall probability of getting a big A, little a, there are two ways to do it. So this is an or statement. You can have a big A sperm and a little a egg, or a big A egg and a little a sperm. So the overall probability of getting big A, little a individual from this gene pool is going to be 2 times P times Q. So we say 2PQ is the frequency of the big A, little a phenotype. Okay, so that's our or statement. We're going to add those together. P times Q plus P times Q, or 2PQ. So that gives us all of the frequencies of these different genotypes. So we want to, still be thinking about these in terms of our cats. So when we're looking at our cats, this is what we're looking at. We're looking at the genotypic frequencies in a population, the big A individuals, the frequency of them, the frequency of big A, and that's going to equal to P squared. We're thinking about the frequency of the big A, little a individuals, and that is going to equal to 2PQ. And then we're thinking about the frequency of the little a individuals, and that's going to equal to Q squared. Now, these numbers are going to equal to each other if we are in Hardy-Weinberg. If we're in Hardy-Weinberg, frequency big A equals P squared, frequency big A, little a equals 2PQ, and frequency little a equals Q squared. So our observed frequencies should equal what we predict from our known allele frequencies if we are in Hardy-Weinberg. And that's how we actually prove that we're in Hardy-Weinberg. Oh, and I, of course, should mention that these should all equal up to 1. And them equaling up to 1, that's going to be true whether or not you're in Hardy-Weinberg, because this is just the frequency of all of the different genotypes, all the different phenotypes in your population. They're going to have to equal up. They're going to have to equal up to 1, right? So again, those little blue dotted lines there, those are going to hold true if you're in Hardy-Weinberg. And we're going to, there's my little double arrow there, that is for our prediction. So we're going to use the frequency of our alleles to predict the frequency of our genotypes, or vice versa. And if the numbers are all congruent, then we say that we were in Hardy-Weinberg.